Yeah, okay. So now we can, I think this was a nice transition because we worked on images, but with a feed-forward neural network that contains linear layers. But actually, these are not the layers that are the best for working with images. And so now we discuss about convolutional neural networks that have convolutional layers that are more suited to work with images. And the reason is that essentially working with images is quite an important field of computer science and computer vision. I took the definition from Wikipedia that says that computer vision is an interdisciplinary field that deals with how computer can be made to gain high-level understanding from digital images or videos. And essentially, you seek to automate tasks that the human visual system can do. So, for example, classifying images, as the handwritten digit example we have seen before. There are many, many applications, for example, image classification that we have seen. These kind of computer vision models are useful on self-driving cars and autonomous vehicles because you need to understand the world that is surrounding the car and that is moving. They're becoming increasingly important in medicine and healthcare, especially, for example, for reading automatically X-rays or tomography data and trying to spot, I don't know, for example, tumors or problems from medical images. And then nowadays we have a big explosion of generative models for images that you can generate images and videos as well. So it's a big, important and current field. It's very challenging compared to like other fields because images are really varied. And for example, here on the right, what's the pointer? On the right, you have a sample of the CFAR10 dataset that we will use later on to play with. And I extracted some of the images of airplanes, and as you can see, they have completely different scales. So for example, this one on the bottom is just a part of a huge airplane, and while this one, for example, is an entire airplane that is much smaller. They have different colors. The objects in the images can come in different orientation, different forms. For example, they're all different planes. They can have a different background as well. So, for example, this seems to be maybe a model because the background is white. Seems to be a rendering. This one is an airplane that is flying, but the background seems to be the ground, so it's green. And while other airplanes are actually in the sky, so the model cannot really exploit the background easily to understand what's going on. So it's a very challenging problem. And yeah, what are images in terms of how you present them on a computer? We have just seen the previous example very well. The grayscale images are simply matrices of n pixel, like you have a height and a width. And yeah, you can represent them as matrices of numbers. And this is for grayscale images. There is only one such matrix that defines like how white or how black is a pixel. And then for color images, you can think them as tensors, but in the deep learning sense, tensors are just like multidimensional arrays. But RGB color image is essentially made of a red channel, green channel, and blue channel. So essentially, this tells you the same information as the grayscale image, so the intensity of the pixel, but for three different color channels. So you can imagine an image like this, a color image, as having a width and height, but also a depth. And the depth of this one is 3, because you have one matrix for the red channel, one matrix for the green channel, and then one matrix for the blue channel. So you can represent the image on the right as a tensor of 3 times number of pixels in height times number of pixels in width. We discussed a bit before about torch vision transforms, which are the way you can transform an image into a PyTorch tensor. And there are two versions now. This is the old one, but essentially you use transform to tensor that converts this PIL image, which is the data format that Python uses. And then you can normalize your data set in order to center it around 0 and have a unit variance. And then there is a V2 version, which changes a bit the way it works, but and I'm presenting both of them because this is the one you should use, but in the notebooks we will probably use both, or before we use this one. And in some notebooks we will use this one, but essentially now you call it, it's called toImage and not toTensor, and then you have to do the conversion from integers. Usually the images in the dataset are integer, but you have to convert it to float and scale it. So with scale equal true, you essentially convert it from the range of 0 to 1, and then you can apply the same normalization that you apply in V1. So first, let's do a back of the envelope calculation. If we've seen the MNIST data set, you have 28 by 28 pixels, but let's consider that we have images that are slightly bigger. They're not big images by any stretch, but if you have 100 by 100 pixel, and this corresponds to 10,000 input neurons because you linearize this 100 by 100 image. And if we just assume that the first hidden layer has 1,000 neurons, do you know how many parameters there are between these two layers? Does anyone want to guess? Yeah, so since there is fully connected, every of the 10,000 neurons is connected to every one of the 1,000 neurons, and so you have 10 million parameters with very simple, like 2 layers. So it's just the first 2 layers. So you can see that we start to have a problem if we go with large images with feed-forward neural networks. And this replies to your question that, yeah, you have to, someone asked this question, but essentially you have to hard code in the fully connected neural networks the input size, and it has a big impact on the number of parameters. So one problem is too many parameters with the risk of overfitting that we will discuss tomorrow. But then the other problem is also like the loss of spatial information. So we have 2D images, and then we go, when we linearize them, we go into a linear representation. And so, for example, we lose information about the neighboring pixels. So if we look at this very green pixel here, it's close to a yellow one. But then if we look at the linearized input, then the yellow one is far apart. So you lose this information that is quite important. It's quite important because usually in images, similar pixel nearby have similar colors as well. For example, if you think about the planes I've shown you before, all the sky is all blue pixels. So it's important to retain this information. So the question is, how can spatial information of 2D images be preserved and exploited in a deep neural network? And the answer is to change the type of linear operation. It's still a linear operation that you do, so basically matrix multiplication. But you have to change the linear operation. It's not like a linear layer in a way that the weights are shared across the pixels, so that you reduce the number of parameters, because you don't have essentially one weight for every connection to every other pixels, but you can reuse most of the weights, leading to a much lower number of parameters. And then another feature is that the pixel of the output only should depend on the neighboring pixel of the input. So a pixel in the sky should not go and correlate with a pixel on the ground on very long range on the image, and this allows you to essentially retain the spatial information. So how do they look mathematically? Essentially, well, it's just an element-wise multiplication between two matrices and a summation. Here you have a part of the image, not the full image, so a 4x4 subset of the image. And then you can multiply it by a weight matrix that, as I mentioned, this is quite small and can be reused on different patches of the image. And we will see this a bit more clearly in a moment. But essentially, this is the operation that is taking place. You take the first pixel, multiply by the first weight, second pixel, second weight, and so on, and then you sum all of them together. So a bit more clearly in images. Essentially, the weight matrix, you can see it here as this 3x3 gray block, and you can see the values of this. This matrix is called, the weight matrix is called convolutional kernel, and you can see in the corner the values of this convolutional kernel. So you have 0, 1, 2, 2, 2, 0, 0, 1, 2. And then in blue, you can see the input image or the input feature map. If you are on deeper layer, it's no longer an image, but it's called a feature map, but it's still same representation. It's like a square array of numbers. And the blue is the input image, and then you can add some padding around it of 0. And then in green, you have the output of this convolution operation. So if you consider the first patch of the image, you compute the convolution that I showed before, so this one, with the image. And so, for example, would be 0 times 0 plus 0 times 1 plus 0 times 2, and so on. And if you look at the number, essentially the only non-zero one is the one in the middle, 3 times 2. You sum 3 times 2 to all the zeros around, and you get 6 as the output. And then you move the same convolutional kernel with the same weights to the left or right, to the right, and then you can also move it down for the whole image. But essentially, you cover these images in patches with the same convolutional kernel, and you do the same operation where you have 0 times 0 plus 0 times 1 plus 0 times 2. And if you look at the non-zero elements, there are 3 times 2 plus 2 times 2 plus 1 plus 3 times 2, and the result is of the summation of all these elements is 17. And so you keep going until you essentially go to the whole of your image, and you get an output. Now, what we're left to answer is like, what does it mean to do this convolution? What this convolutional kernel does? And so we can look into an example where we have an image on the left, and we apply a convolutional kernel that has been handcrafted. So we decided to take a convolutional kernel of 3 times 3, so same size of this one that we used before. And essentially what we do is that we multiply, we do the convolutional operation on the whole image. So we go to the first patch, multiply all the pixels of the first patch by these numbers, and sum them together. And we continue doing that. And from the structure of this, this filter, you can already see quite easily that if you have pixels that have more or less the same values, because this is like a very uniform piece of the image, you will have, well, positive and negative in the opposite side. When you sum all these pixels that have the same value together, you get 0. And so what happens is that if you apply this filter, you get this image as output, the filtered image, and essentially what happens is that the borders are highlighted. So where the background is uniform, you get essentially 0 everywhere. For example, on the sky and also on the grass, there is a bit of noise, so you see a bit of structure, but essentially it's all washed out. But then you can still make out really well the borders where the intensity of the pixel changes. For example, the man and the tripods. And this convolutional filter has been used for a long time for working with images and, for example, extracting edges. So this is called Sobel filter and is an edge detection filter. It's quite a famous one. But essentially, the idea of convolutional neural network is that you can apply many, many filters to get from your original image a feature map that has some specific feature. But the clever bit is that convolutional neural network learn this filter. So this filter is the learnable parameter, is your weight matrix that you learn during training. So essentially, the convolutional neural network, what they do is that they learn these convolutional filters in order to extract from an image a set of features. And you can, instead of having one filter like the one we have here, you can have multiple filters that you apply to the same input, and then you get multiple feature maps as output. Now, we have seen that essentially we get some interesting information out of convolutional filter. We get feature maps that can be learned. Because by construction, it takes into account neighboring pixels. So we have that the spatial information is kept. The spatial information is kept. How do you say? Well, cluster and close together. Yeah, it's preserved. Thank you, John. And so the last question is how many parameters? Like, did we reduce the number of parameters with this or not? But we have a question first.
Yeah, it's related to 2 slides before that you were just showing. Why do you move the filter matrix 2 pixels by 2 pixels? I didn't get that.
This is a very good question. So you don't have to. This is another hyperparameter of your model. You can decide how many steps your filter you want to do. So in this case, I'm just showing an image for 2. So we start here, and then the next one will start here. But this is something that is parameterized in your model. And I will show it later. It's called the stride, and it decides how many pixels you move your filter on. Usually, in the first notebook, we will use a stride of 1. So usually you move only of 1. And the reason of moving only of 1 is that if you choose the right padding and you move only of 1, you can retain the same size of the input. So you don't change the size by doing the convolution if you choose the correct padding. While here, by switching of 2 pixels, so we have a stride of 2, you can see that the output image is 3 by 3, while the input image is 5 by 5. And this will be exploited tomorrow in the generative models. But essentially, if you want to lower the dimension of your input, you can choose a stride larger than 1. And if you want to keep the same size of your input, then you choose a stride of 1. So this is just an example, but it's a very good question.
Can you please briefly explain again why you need the frame of zeros? Why would you need to go to a larger dimension to a lower dimension? I did not really get that.
Sorry, what do you mean? Like, why I put zeros here?
Yes.
I mean, again, this is a choice. You can choose if you want to add padding and how much padding you have. But for example, if I go to the first slide, your filter always starts the convolution on the top right. So if you have a 3 by 3 convolutional filter like this one, and you want to keep the size the same, you need to add padding so that the first actual pixel of the image is centered in the filter. Because then you're doing multiplication and summation. So from the filter, from the convolution of the filter and the image, you get a single number. And so that single number would be put in the output in this position. And then if you go the stride by 1, this is 2, but imagine that we went stride by 1 2 times. Now you take the average of all this, and then you put it in this pixel in the center of the filter, essentially. Yeah. So you need the padding to shift the initial state of the filter on the top leftmost pixel here. And in that way, you conserve the size of the image, because then when you go all the way to the left, you have the same padding on the other side. And then when you sum all together and you convolute, and then you have one single output out, you will get it in this position. And so you have the same size. While here, we are doing a stride of 2. And essentially, if we didn't have padding, we would start lower, and we would have 3. And then, we will only have an output of size 2 by 2. Because you have, I don't know. Maybe it's easier this way. But essentially, if you have, this is your 5 by 5 image, right? And you start your 3 by 3 filter without the padding. So the first filter will be here, right? And then the second filter, you have a stride of 2. So you move it here, and you will have your 3 by 3 filter. And so your output would look like this, and then this. So you go from a 5 by 5 to a 2 by 2. And then with padding, you go to a 5 by 5 to a 3 by 3. And you can play around with this dimension to have essentially the size of the output that you want. Yes, that's also an hyperparameter of the model. And if you have a bigger filter and you want to compute to keep the image size, for example, if you have a 5 by 5, then you need to add a padding of 2, because you will start, the center will be 2 pixels left. So this is all parameters that you can play with when you build your model, essentially. Yeah. Mm-hmm.
Does it mean that the neural network in training decides the size? Something that you, let's say, selecting the architecture of the neural network and then like a constraint that you put for the kernel?
Yeah. So essentially, maybe we didn't explain this well, but when we say parameter of the model, those are the parameters that are part of the model and are trained during, that they're modified and changed during training. And for example, the parameter here would be the convolutional kernel. So that's your weight matrix that you use to convolute. Then you compute the gradients of the loss function, the loss function with respect to this weight parameter matrix, and use that to update the parameter. When we say hyperparameter, is still parameters of the models, but they're not changed during training. So there's hyper because they're like one level up, if you want. And you can still do hyperparameter optimization. We will not go into this into this course, but essentially those are parameters that you can optimize. One way would be to test different values. There are more advanced techniques, but you can test different values of the size of the convolutional kernel and see which one is better for your model. But this is something that is fixed during training. So hyperparameters fixed during training and are part of your design decisions, essentially. Other questions? Yeah.
One more question. Is it a given that the size of the output is exactly the same as the one of the convolutional kernel? That you have like a 3x3 matrix?
Oh, no, that's just the example.
Ah, okay.
Yeah. I mean, you could have the same convolutional kernel. For example, here, the example that I show here, I have a 3x3 convolutional kernel. I didn't add the padding, and so the output will be 2x2. And if you have much larger images, that is usually what you work with, then the output is usually much larger than the size of the kernel. Yeah, because you apply the kernel many times in many different places. Yeah.
Yeah. So if I understand it correctly, the reason that we use this convolution method, because in a fully connected system, there are too many parameters, and when we change it 2D to 1D, we lose information of
Yeah.
the neighbor.
Yeah.
But what if all the pixels are intercorrelated? And in this case, can you still apply this convolutional method? Not just the neighbor, but the entire system.
Yeah, I will show later that there is another component to convolutional neural network that actually reduces the spatial size, and so you add longer range correlations. I will talk a bit about this later. Yeah. Is clear? Okay. Then we can do the same back of the envelope calculation with a convolutional neural network. And again, this time, I mean, they're not really comparable as calculations. But this time I use color channels as well to show you how to compute it with color images. But essentially, the input is 3 color channels, red, green, and blue, times 100 pixel times 100 pixel. And then if we choose a convolutional kernel of 5 by 5 with a bias unit, the bias is again like the shift that you also apply in the linear layers. You have the same in the convolution. So essentially, you don't have only, you don't have only this, but you also have a plus bias unit that you can turn on or off. Again, this is a hyperparameter, so you can decide if you want to have it or not. And then the output, we can say that we want 200 feature maps. So it means that instead of applying one filter to the image and get a feature map out, we apply 200 of those filters. And every one will be slightly different, and the model will learn how to use, we learn those 200 filters in order to do the task that has to learn. So essentially, we have 200 feature maps of 100 by 100 pixels. So essentially, yeah, we extend the depth dimension and keep the spatial dimension fixed. So spatial dimension input and output is the same, but then we have 3 colors channels that goes into 200 feature maps. And so if we do the calculation again, in this case, the number of parameters is 5 by 5, which is the size of the kernel. And then the kernel also has a depth that uses all the channels. So for input of 3 color channels, you have a size of 3. So your actual kernel parameter will be 5 times 5 times 3, plus 1 bias unit. And then you have 200 of them, because you want 200 outputs. And so if you do the calculation, it's 15,200 because of the bias unit. If you remove the bias unit, it's just 15,000. And you can see we have like orders of magnitude less parameters with this kind of architecture. It's just essentially a summation weight that you add after here. Just a plus bias is another parameter of the model. Like in the linear layer, you have your weight matrix times your input plus the bias. It's just a shift, essentially. If you don't use the bias, well, it really depends on your model. But for example, we were discussing before in the example, in the notebook example that we had, the linear layer, we were trying to essentially learn a linear function, right? So we have, can you see? Yeah. Yeah. So you have your x and your y, and the data was actually centered at 0. And so in this case, you can fit the model as wx plus b. So w is your weight and b is your bias, right? And in this case, it works without the bias, so you can leave it because your data is centered at 0. But if you have the data that is shifted, for example, here, well, then you cannot use WX to fit the model. Because WX would like give you something here. And so you're missing this shift.
That was a linear model with a convolution operation.
Yeah, but it's still a linear operation. So the concept is the same. Yeah. I mean, here is much easier to visualize. But essentially it's a shift on your output that the model learns. Maybe learns it to be 0 in some cases. I mean, if you fit this and you look at the B, did we look at the value of B? Was it 0? I guess so. Yeah, so it learns that the BIOS has to be 0. Well, minus 1, yeah. Mm-hmm.
So 0 is like middle color, yeah.
Yeah. Is it clear? Yeah. Okay. Let's go forward. Yeah. Essentially, we said that we have a lot less parameters with this architecture. So this architecture is really good for working with images. That's the conclusion. Then there was a question about long-range interactions between the pixels. And actually, we are missing one ingredient in the architecture that is called pooling layers. But essentially, you can see here, this is the prototypical architecture of CNN, where you have your input image, 32 by 32 pixels, sorry, it's a bit small, and one channel. So this is the number of channels, 1. So it means that it's a grayscale image as an input. If it was a color image, it would be 3. And then you go from 1 channel to 6. Here they have a size of 28, which means that they probably choose to not use the padding. I didn't do the calculation, but either they didn't choose, I think they didn't choose the padding. I don't know the size of the convolutional kernel, but the size is reduced a bit compared to the input. But then you also wanted to reduce it by more. And you can pool, so you can take, for example, the average or so of some of the pixels, or you can take the maximum of some of the pixels. So essentially, your output of the pooling layer, I think this slide should have been later on, but yeah, I will show the actual pooling layer in a bit. But essentially, the take-home message for now is that you have a spatial dimension that is reduced. So the height and width of your image are reduced in a way that you pull together some of the neighboring values. And so when you apply the second set of convolutional filters, essentially you are having longer range correlations because you are using results of multiple pixels, and now pixels that were a bit far apart are closer together. We'll come back to a proper visualization of this in probably the next slide. Then you have activation functions as usual, because convolutional operations are linear operations, and so you need nonlinearities in order to learn nonlinear functions, as we discussed this morning. And then at the end, when you have a bunch of feature maps you're happy with, you can linearize, not the input, but the feature maps, and then apply a bunch of, like a fully connected neural network to do the classification, exactly as we were doing this morning with the MNIST dataset. So this is the architecture. And then, as I mentioned before, there are some normalization layers that try to help with the training and normalization of the data. So in PyTorch, convolution looks essentially like this. There is a convolutional layer that is torch.nn conv2d for 2D convolutions. You can also do convolutions in 1D, 3D, like generalized to any dimension. So you can also work with volumetric data, for example, it's really good. But you might have also some one-dimensional sequences that can benefit from this architecture. And you have to specify the number of input channels. For the first layer, this will be always 1 for grayscale images, or 3 for color images. And then the output channels is the number of feature maps that you want. So it could be like 128, 64, 3000, whatever. Again, hyperparameter of your model. So you have to design your model. Is a design decision of your model. Then the kernel size that we've seen, and then we already discussed about the stride. So how many pixels are you moving your convolutional kernel? And then padding, how many zeros you're adding, lines of zero you're adding around your image. And dilation, we'll come back to this tomorrow, but it's not super important, but essentially it's the spacing between the elements of the convolutional kernel. So you could have, like the convolutional kernel is not a square patch, but has spaces between the elements of the kernel. But we'll come back to this tomorrow. Then you can choose the BIOS unit as usual. And I think I never used this one, but it was in TensorFlow, and now it seems to be in PyTorch, but instead of having to compute the padding yourself, you can, I think, you should test it, I haven't, sorry, but I think you can put padding equals same, and he adjusts the padding in function of the other parameters to have that the output size is the same as the input. So it's just a convenience that before, that was in TensorFlow, and in PyTorch you had to do like this kind of calculations and look at the size of your kernel, but now you can use this padding equals same to have the output same size as the input. And yeah, now we're back to the pooling layers, but essentially, as I mentioned before, you have a pooling kernel, and again, it's the dark area, and you can choose it. You can choose the size of this pooling kernel. You have a max pooling 2D or average pooling 2D. Max pooling essentially takes the maximum of the image within this patch. So in this case, we have 3, 3, 2, 1, 2, 1, 3, 0, 0. So the maximum is 3, and so your output is 3. For the average, it's the same concept, but you take the average of all this number, and then it's 1.7. And then you move. Again, you can decide how much you want to move with the stride parameters. Here I move of 1, but usually you move of stride of 2 because you divide the size of your image by 2, essentially. So you take 1 pixel every 2, if you have a kernel size of 2. So usually you use kernel size of 2 and stride of 2. That's a very common choice. And so you have 4 pixels become 1, and then you move again. 4 pixels become 1. And then you divide your size by 2 in each dimension. Yeah, and essentially works similarly to what the convolution does. You pass this pooling layer over your image, and you compute the output image. And then activation function ReLU is very commonly used, and we've already seen it, so we can probably skip this one. So what a convolutional neural network, very simple one, looks in PyTorch. Essentially is a series of convolutional ReLU activation function, and then this is one layer, and then you have a second layer of another convolution, pooling ReLU. And then, as I mentioned, you can flatten all your feature maps that have been learned, and then pass them to a linear layer that outputs, for example, if you're doing a classification task, the number of classes. And here I didn't subclass the NN module, as I mentioned before. There is a convenience function in PyTorch if you have a sequential model, so that the output of one layer is passed straight to the input of the next layer, and you can use this NN sequential class that essentially is a shorthand for building this kind of sequential model. But here you can see convolution. You go from 3 channels, which are the 3 color channels for a color image, to 16 feature maps with a kernel size of 3. Then you divide, you do the pooling with a 2x2 kernel, apply the activation function, and then you go from the 16 layers to 16 feature maps to 32, and then you flatten. And this flatten essentially does the same thing that we have seen before with the view function. So essentially flattens all the dimensions apart from the batch size. Oh, I had a slide actually. I think I added this late yesterday evening. But yeah, this is essentially what I mentioned. What the flattened layer does is that you can have an input, which is a random tensor of 1 by 5 by 5, 32 by 1 by 5 by 5. 32 in PyTorch is always the batch size. So the first size is the batch size. Second size is the number of channels. So 1, again, grayscale image. And then is an image of 5 pixels by 5 pixels. And for flatten, if you use the default parameters, it says to start flattening to the dimension 1 and end flattening to the dimension -1. It means that it leaves the first dimension untouched, and then it flattens everything else. And this is, again, a layer that is derived from the NN module. So you can call it with the brackets. You define M as NN flatten, and then you can call it on your input, get the output, and if you print the output size, it's essentially 32 times 25. So you flatten your 1 by 5 by 5 image into a 25-dimensional vector, leaving the batch size unchanged. And you can do exactly the same thing with the view that we discussed before. Is exactly the same thing, but the flatten is very convenient to have in the NN sequential API. Otherwise, I always use the view if I'm defining the forward function manually. So now we can go through a bit of like history of CNN architectures. We will not see all of them because there are so many. But one of the first one was the LeNet 5 architecture. It's quite old, actually, from 1995. And it was designed for the classification of handwritten digits in the MNIST dataset, which was like very popular, but now is kind of superseded because considered too simple. And we have seen that because we can fit it with a feed-forward neural network with, what was the accuracy? Like 97, 96. So very good accuracy with a feed-forward neural network on this dataset. So it's not very representative of images. Also because like the numbers are all nicely centered and rotated all in the same way. So it's really pre-processed, and it doesn't look anything like the data set that I showed you with the airplanes that are completely different. The input is 32 by 32, grayscale images, and has 2 convolutional layers, 2 subsampling layers, 2 fully connected layers, and then because you're doing classification of 10 digits from 0 to 9, you have a softmax activation function at the end that gives you the probability of each class. And this is the architecture that is already the one that I showed before. You have the convolution in orange, the pooling layer in red, and then you have the linear layer in green. Another very famous architecture, and this one won the ImageNet competition, which is much more challenging competition than the MNIST dataset on real images. And there are 1,000 classes, so not just 10, but it's much more challenging dataset, 1,000 classes. The size of the images is much bigger than what's in MNIST, and there are color images, so this is why there are 3 channels. And well, the architecture is kind of similar. There are convolution, fully connected layers, ReLU activation functions, and then there is something that is called local response normalization. That is essentially a normalization to stay within the range of sensitivity of your activation function, which is not needed in ReLU because ReLU do not saturate, so the input is not, the output is not squashed between a range, and the gradient of ReLU is essentially constant. While, for example, if you use a sigmoid activation function, the gradient of very extreme values is essentially 0. And so it's a pain to train. And this normalization essentially tries to put the range back into the sensitivity range of your activation function. This is the architecture. As you can see, they're getting deeper and deeper. This is essentially where the terms deep learning comes from. But you go from like your input image to 36 feature map, 256, and so on and so forth. And then again, you pass through the pooling layer and the softmax activation function. And in terms of local response normalization, what this normalization does is that it normalizes on the adjacent feature maps. So you can imagine as the 3 color channels, when you have multiple feature maps, that's the depth dimension. And so you normalize across these feature maps, but only the neighboring one. So this is again, you have to choose how many neighboring feature maps you want to consider, but essentially you take the activation of a specific feature map and you rescale it. You can see the minus exponent, so you divide it by the sum of activations, squared of activations of neighboring layers. And this essentially is a competitive normalization because it tries to inhibit strongly activated neurons. The strongly activated neurons inhibits other neurons. So if you have feature maps that are strongly activated, so I have a high value here, then the feature, like neighboring feature map have a high value here, then the output of the current feature map after normalization would be low. And this essentially encourages the network to learn a wide and different ranges of features. So the filters are not all the same, but they're learning very different features, and it improves generalization. They show in the paper.
I'm not sure I fully followed. Are you saying that if a particular feature map has a strong activation for a particular position,
yeah,
then when the normalization kicks in, then the other feature maps are effectively being ignored?
Yeah.
And so it's just normalizing with respect to, so that it maintains a larger value and it isn't pulled down by the other. Like,
no, so if the other ones, if the neighboring feature maps are activated by the same, are activated in the same way and they're large, then the current feature map is actually divided by a large number, so it becomes small.
the current feature map.
Yeah. So this is across like the depth dimension, the feature maps, and it's done for each pixel essentially of the image.
Only for the pixel being queried, not for the whole feature map, just for that one pixel.
Yes, yeah, exactly. Yeah. And then another architecture is quite famous and popular, and we will use this for tomorrow for transfer learning. It's called VGGNet, and is I think the first convolutional neural network where they stack the convolutional layers one after the others, and is a runner-up. It's not the winner, but it's a runner-up of this ImageNet competition, which is classification of 1,000 images. And this is the architecture it looks like. So it's different from the ones before, but the same components, where you start with some convolution, then pooling, a bunch of convolution, pooling, bunch of convolution, pooling, so on and so forth. And then at the end, you have you linearize the feature maps and then fully connected layers and output. And then another one that is interesting to look at is ResNet. Again, there are many variants. 34, 50 is the number of layers. So you can see that they're getting really deep with 152 layers. So this means that your sequential model will have 152 conv, max pooling, and whatever. So they're much deeper. And they use a technique that is called batch normalization. So it's another normalization technique that allows you to have a higher learning rate and is less sensitive to initialization. Because maybe we didn't really mention this, but the weights are initialized. Oh no, you mentioned. But the weights are always initialized at random. And so sometimes the distribution that you choose to to initialize your weight has an impact on the initial state of the model, and so the training. And we will come back to this later tomorrow. And then act as a regularizer. It means that it prevents the model a bit from overfitting. And this was the winner of the ImageNet competition in 2015. And this is the architecture. Again, quite similar, but you can see that they have some blocks that are repeated, for example, 23 times. So that in PyTorch, you would define this as a block, as an N module that does this specific thing. And then you can repeat it as a sequential in like 23 times, 3 times, 4 times. So essentially, this architecture is built in different building blocks. One thing that is quite interesting is these green lines here, which are called skip connections. And what it means is that you take the input, you pass it through the block, which consists of some convolution and some pooling, but also you store it, and then you add it back to the output. And this is what it looks like. Normally, you have this situation where you have input, you pass it through the layer 1, and you pass it through the layer 2, and then you get your output function. But with a skip connection, you have input, pass it through a layer 1, pass it through a layer 2, but then you also have a second path in your computational graph where you essentially take the input and sum it back to the output. And this essentially allows you to speed up the training because what this block is learning is close to the identity function at the beginning, because if you initialize your neural network with random weights, this function is probably, well, it's going to be close to 0, and so the output of the layer is actually going essentially is the input. And then the other thing is that it facilitates signal propagation, because when you do the backward pass, you essentially have you're applying the chain rule over and over and over again. And so if you have small gradients and you only use this one, essentially by the time you go to the higher levels of your neural network, the gradient could be very low and very small, and so these gradients have difficulty, these layers have difficulty to learn because the gradient is small, but by adding the skip connections, essentially you can skip the whole block that maybe needs a bit more time to train and propagate the information backward to the other layers. And implemented it in PyTorch is quite simple. I just took it from the official implementation in Torch Vision, but you have your forward function for this block, so for these 2 layers. You take a reference to the identity, and then you pass it through first convolution, batch normalization, ReLU, convolution, batch normalization, and then at the end, when you have here you're modifying your output, but when you have your output, you just sum the original input, and then you apply the activation function again, and that's your output. So in this case, for example, it's one of the cases where it's important that the convolution do not change the size of the input, because you're taking a reference to the input and adding it back, so it has to be the same size. And this batch normalization is quite interesting, but essentially you compute the average of your batch across the feature and the height and weight, and you also compute the variance, and then you normalize your input. But you don't just normalize your input, you also have these gamma and beta parameters. So you take a linear map of the normalized input, and these 2 are parameters that are trained. So the expectation value and the variance are computed with the data that you pass in your batch, but then these 2 are parameters that are learned. And this is the first layer we see that has a different behavior when you train the model and when you evaluate the model. We discussed it before, that you have to do model.train when you put the model in training mode, and model.eval when you put the model in evaluation mode. And the reason are layers like this one. We will see another one tomorrow. But essentially, the problem when you do inference is that you could pass a single image. And then a single image, what you average on, like you average on itself, so this is 0, and your output it's 0. Well, it's beta if you have beta learn. And so what this layer does during training is also that it keeps a running estimate of the expectation value and the variance into variables, internal variables in this layer, mu and sigma square, and is an exponential moving average that is updated as the training goes on. And when you do inference, essentially instead of computing the actual average and variance of your batch, you just use these estimates that have been tracked during the training. And so when you put the model in training mode, essentially this is used. And when you put the model in evaluation mode, instead of E and variance, it uses the running estimates that kept track during training. So it's really important to put the model in training and evaluation modes if you have these kind of layers. If you don't, like the previous linear layer, nothing changes. In PyTorch, it's quite simple to implement this technique. You just use batch norm 2D, and you pass the number of features that are the output of the previous channel. And yeah, that's pretty much it. I mean, there are other parameters. Momentum affects how the running average is updated, but usually you can just set the number of features and use it. Yeah, the advantages of this technique that's been shown in the paper that published it, I'm missing the reference here, is essentially to greatly reduce the vanishing gradient problem, which is what I mentioned before. If you have sigmoid or tanh activation function that saturates, so that means that like they give essentially the same value for every input, if your input is high or very low, then the gradients are essentially close to 0, and this prevents this problem by normalizing into the sensitive range of the activation function. Then they show, I think empirically, but I'm not totally sure or if they did it mathematically or empirically, but it reduces the sensitivity to weight initialization, so you don't really have to care too much about how the weights of your neural network are initialized, and allows the use of larger learning rates, so it speeds up training and acts as a regularizer as well. We discuss about overfitting tomorrow, but essentially it's like a great layer to put into your models. Then there are so many more CNN architectures that we have not discussed. You can search the literature, that's plenty. Everyone's slightly different, and try to improve a bit on the previous one. But essentially, this is a question that has been asked before. But what I would do if you have a project is to try to look at the different architectures, see which one is best for something similar that you're trying to do, and start from there, and then probably optimize the hyperparameters for your particular task, and try maybe try also different architecture and see which one performs best. But essentially, you have to play around a bit with the different architecture for your specific task and see which one is most useful for you. And then finally, I want to mention this because it's a bit outside of the box. But this is something that I've been loosely involved with, not so much in the design, but more in the implementation of the software in some cases. But essentially, one cool application of convolutional neural network has been found in protein ligand docking. And protein ligand docking, if you're not familiar with it, is essentially the computational tool that allows you, given a protein target, and a small molecule drug to find, generate plausible conformation of this drug within your protein, within your target, and rank the plausible conformation according to like more plausible to less plausible. And the group of David Coase at the University of Pittsburgh came out with this idea of trying to apply convolutional neural networks to this problem. And so essentially they took an input, molecules, that has nothing to do with images, but then they generated some volumetric data that represent the atom position in space, in a three-dimensional space. And they have, instead of colors, the different atom types. So carbon is essentially one channel, and then another channel is nitrogen, another channel is sulfur. And so instead of using colors and images, they use volumetric data representing the atomic position in space, and they use, instead of colors, the atom types. And they applied this to docking, and they showed that using convolutional neural network scoring function can actually improve on the state-of-the-art classical docking software results. So I think it was quite interesting to show that you can apply CNN also to fields that are not just images if you convert your data in something that the CNN can understand. It's about it, but we missed a lot of stuff because, well, I mean, the field is huge. What we missed, for example, is localization, which is the task of finding not which object is in an image when you do classification, but where the object is located. Which object, but also where it is located. If you have a single object, you can actually change your final layer of your convolutional neural network and cast it as a regression problem instead of a classification problem. And the output would be essentially 4 numbers: the center of your bounding box, the height, and the width. But then it becomes much more complicated when you want to do object detection, and you have essentially this problem of localization, but with multiple objects. So for example, if you have an image from a camera of a self-driving car with a lot of pedestrians, you want to localize all the pedestrians, not just one, hopefully. And there are specific architecture also based on convolutional neural network, but then you have to do some more clever things than just a sequential model to classify and localize the object. Then another big topic that we skipped is semantic segmentation, where essentially you don't want to classify, to put an image in a class, so classify the image, but you want to classify every pixel of your image. And so you get a segmentation mask where some pixels are colored in the same way and represent, for example, a building, and then some pixels that are colored in the same way represent a bridge or a car. So essentially you do a classification on every pixel, and again here you use convolution, but you need some special architectures. And then the final one that is worth mentioning is the vision transformer. That is one architecture that does not use convolutions. It's quite new, but it would be interesting. Well, we will not be discussing it, but it is related to the transformer architecture that we will see in the last day of the course. Yeah, so that's it from me. What we can do now is do the exercises, and for the exercise, essentially we have a similar notebook to the one we just saw for the MNIST, but in this case you have to implement a convolutional neural network, and for classification of CFAR10, which is a set of color images with 10 classes, and is a more challenging data set than just MNIST. So yeah, we can probably go through the notebook in a bit together just to show these steps. But the way I structured this notebook is essentially I prepared everything and then cut out some bits that you will have to essentially fill in yourself from what we have learned in this lecture and the previous one. Yeah, that's it. Do you have any question? Yeah. Yeah.
So maybe I missed it, but on the batch renormalization part,
yeah,
those, since it's a part of the it's part of the layers, is this epsilon, gamma, and beta are parameters or hyperparameters?
It's a good question. So epsilon is a hyperparameter because essentially we set it here. So it's essentially an input. When you define the model, what you put as an input is usually an hyperparameter because you decide what to put as an input. Here, he has a default value, but you can, you can change it, but it's a fixed thing during training. And it just serves not to divide by 0 if you have 0 variance, essentially. While gamma and beta, these are parameters. So these are learned during training. So the autograd will compute the gradient of the loss function with respect to those parameters, and then when you update, when you do the gradient descent step, the optimizer will update these parameters with the gradients.
In this case, the loss function would be some kind of checking if you have some vanishing gradients to adjust gamma and beta so that...
No, the loss function will be the loss function of your final layer. So if you're doing a classification task, it will be the cross-entropy loss. And then the gradient will be computed by autograd automatically of the loss function with respect to this one. Because this layer will be into your forward pass, so your loss function implicitly depends on these parameters. Okay, so we can go through the solution. I hope it wasn't too bad. Do you have a question about the data set or how to load it, mini batches and stuff like that, or that part is clear? Yeah, so essentially what we did is to convert the data into a tensor. Maybe a bit bigger is better. Okay, let's close this one. Yeah. We converted the data into tensors, so something that PyTorch can use. And then we have this normalized transformation that essentially just take the input, remove the mean, and divide by the standard deviation for each of the channels. And this transforms the range of the images from 0, 0, 1 to -1, 1, which we discussed before. Then we downloaded the dataset, the CFAR10 from the Torch Vision dataset. And then this is something we did not really discuss in the lectures, but you should always set aside the test set for final testing on the train model, and we will see a bit more why tomorrow. But essentially, you can extract a sort of validation test, is called, from the training data. And so you split your training data into two subsets, and then you can have this random subsampler that randomly subsamples the two data sets based on the indices that you have here. And so this does the shuffling. This is why we didn't use the shuffling here, but because it's sampling randomly on these indices on the fly. And then once we have this, we can define the data loaders as we did before, and likewise for the test set. So at the end, we have a training set, which is what we use for training, a validation set, which is what we use for validating the model during the training, and then at the end we have a final test set that is never been seen or used by the model, and that's where you test the final trained model. And the reason why you split the validation set, we will see it tomorrow morning, but essentially is that you can use some information of the validation to improve the training or stop the training. And so that's something that goes into the training of your model. And in order to avoid spillage of data, you need to leave the training set completely separate. Then this was just for visualizing the data. The only probably trick is that you have to undo the normalization transformation that we did, because essentially we load the image with this transformation, but if we want to plot them with matplotlib, we want to revert this transformation. And then another thing is that PyTorch has channel height width as dimensions, while matplotlib expects the channel as the last dimension, and so you have to transpose your data in order to visualize it with matplotlib, just because they're using a different convention. Then in terms of convolution, probably this was the hardest part, and it's usually the hardest part of building the model, figuring out the dimensions. In the class, we have seen, and I kind of mentioned that if you have a 3x3 kernel or an odd kernel, you want the center of the kernel to be on the first pixel of the image in order not to change the size of the output. And so you have to choose the padding in order to do this shift on the topmost pixel. And so for a 3x3 kernel, if you add a padding of 1, so you add zeros in one dimension up and left, and also right and down around the image, you add one line of padding. This combined with a 3x3 kernel doesn't change the size of the image. And then apologize, probably it wasn't specified too well that the maximum pooling layer, the goal was to divide the size of the image by 2, so the spatial dimension. It was kind of hinted in the assertion that I sprinkled through the forward pass, but I should change the notebook to make it clearer for sure. But yeah, the goal of the maximum pooling layer in this convolutional neural network is essentially to divide the size, the spatial dimension of the image by 2. And so you start with the input, which has 64 batches that we hard-coded, and this is, again, hyperparameter, so you can change it, but it's not optimized during training. It's just a fixed decision, and here we just choose 64. And then you have 3 input channels for the 3 different colors, because we're dealing with color images compared to before, where we had only grayscale images with the MNIST dataset. And then the size is 32 by 32 pixels. And then when we apply the first convolution, because we choose the padding accordingly, in a way not to change the dimension of the image, the only thing that changes is the number of channels. So you go from 3 channels to 16, but you still have 32 by 32 pixels. And by the way, someone used padding equals same, which was a very nice shortcut not to have to figure out the padding. So you can, as I mentioned on the lecture, you can do padding equal same, and then you don't have to worry about what to set the padding to. Is computed automatically by PyTorch. So that was a trick that you could have used to simplify a bit the calculation that are really quite annoying, because you have to get the dimension through the whole network. And then again, you apply the pooling. And so in this case, you leave the number of channels the same. So 16 goes to 16, stays the same. And then the size of the image is divided by 2, because you're using 2x2 max pooling kernel with a stride of 2. And then you repeat this a few times, and then you get, at the end of, after the last pooling layer, 64 channels, and this is the output of your last convolutional layer. And then because you apply 3 pooling layers, the final size of the image is 4 by 4, and so you know essentially that you have to reshape with a size, linear size of your feature maps, 64 by 4 by 4. And then after that, you use these linearized feature maps to pass into a feed-forward neural network, and you predict the number of classes. one thing here, maybe I should have changed this as well. Maybe it was not so clear, but you can either output the last linear layer directly, and then use the cross-entropy loss, as we did for the MNIST dataset. But if you look at the documentation of the cross-entropy loss, essentially it says that he applies this function and then the negative log likelihood loss, which is a different loss that is provided by PyTorch. So in this notebook, I decided to go for adding the log softmax as the last input, the last output of the neural network, so that you can get the probabilities by doing torch exponential, and you immediately get the probabilities. Is this clear, or yeah?
What's the difference between using f dot value or f dot softmax or n dot value?
So this is a very good question. The NN are all subclasses of the module class, and you can define it in your constructor of the model. However, what you really want to define in the constructor are the layers that have a state. So the convolutional layer have a weight associated, like the convolutional kernel that you're learning plus the BIOS, and likewise for the linear layer. So you want to define them as like classes and then use it because they contain parameters and stuff like that. The max pooling layer as well, but also the ReLU layers, they do not have any state. They're just like, the ReLU is just, for example, is just a function that you apply to your output. And so you don't really need to store an object in your construction and then apply it, but you can simply apply the function. And PyTorch has a whole functional API where you don't have objects that store the parameters inside, but you can pass the parameters explicitly. This is also for the convolutional. So there is a functional convolution where you pass the input size, output size, kernel, weights as well. But for the activation function, you don't have to pass anything because they don't have any state, essentially.
We don't have any weights. It doesn't make a difference whether we use f dot and n dot, but we don't save objects, so it's better to use f dot.
I mean, it's not better. It's just like easier because you don't have to define something. Yes, yeah, they do. They're completely equivalent. And I can show you the functional API for com2D, just so that you understand. Essentially, the functional API is under nn.functional, but is a functional API in the sense that you apply a function, but there is no hidden state. And in this case, you can also use it for the convolution, but you have to pass the weight, essentially. And this means that you have to define the weight into your constructor of the model, and yeah, it's just more faff. But for simple function like the activation function, it's usually quicker to use the functional API. But they're completely equivalent, and you can use both. Do you have any other question on the model? So this one, the view, yeah, essentially you need, so one trick you could do is to place these assertions. They will fail, and if you put comma and shape, they will also print the shape. So you can actually use this when you build your model. It's a small trick, but you can compute the size depending on which convolutional layers you applied and which pooling layer you applied, and you end up with 64 batches. This is your batch size, but then you end up with 64 channels, which is the output of the last convolutional layer. So this is what you decide to output from the last convolution. And then because of the 3 max pooling, you have 32 a size of 32, then you do max pooling, you go to size 16, then you do max pooling again, you go size 8, and then you do max pooling again, and you go size 4. And then with this, you linearize essentially your feature maps into a one-dimensional vector for each batch. So it's still a matrix because you have the batches in the first dimension, but then this, you can pass it to a linear layer, which expects this dimension. It's good.
That means that we could have a maximum of 16 things, yes?
That you could have a maximum of?
Well, we've got 10 objects in our kind of cat, dog, chair, whatever it is, I can't remember what's in it. If that six, if we made it, if we max pulled it again down to 2 by 2, we'd only have 4 actual output classifiers in the end.
No, but because you multiply it by 64, yeah, exactly. Yeah, I mean that they are part of the features that you output. Yeah. And I think in one of the exercises tomorrow we will actually go down to the space dimension of 1 by 1, but then you have the channels, and then you can reinterpret that as essentially a number.
Because if you're doing a kind of feature detection, and then you're doing another, and you're passing it through these subsequent convolutional layers, then by the time you get down to 4 by 4, it's a pretty dense bit of. Do you know what's in those?
Well, there have been some attempts to show the convolution, what they learn and what they are activated by, but they're usually on the top layers. Then on bottom layers, it's very difficult to interpret. Well, yeah, I mean, the first layer learns simple, essentially the features that you learn is something similar to the Sobel filter that we've seen that essentially gives you edges or lines. And then the second layer essentially uses those features and combines them to have more complex features. But then after a while, it's very difficult to know what's, yeah, you cannot really visualize it anymore. Any other question about the model? Okay. Then we just move it to the GPU. And this probably, John, is the question you asked this morning. You can define the device. If you have the GPU, you use it. If you don't have, you just use the CPU. So now these notebooks, you can run it. If you run it on Daint, it works on the GPU because CUDA is available. If you run it on your local laptop and you don't have a CUDA capable device, then it will run on the CPU automatically. Then, yeah, here you show the class probabilities in order to show the untrained model. I think this should be quite clear. The thing that I was mentioning before, if you have the log softmax output, you take the exponent of the output of your model and you just get the softmax because you're inverting the log. And so this is just the probability of your class. And for the untrained model, they're all 0. And then, yeah, since we applied the log softmax, the correct loss function to use is the negative log likelihood loss. But as I mentioned here, essentially is the same, exactly the same as the cross entropy loss applied to the raw output of a linear layer. And the documentation says that essentially cross entropy loss internally applied the log softmax and then the negative log likelihood loss. Then you have optimizer and the training loop. I think we've seen it many times and probably we'll see many more tomorrow. But yeah, you move the data to the GPU, reset the gradients because PyTorch by default accumulates the gradients, so you have to set them to 0. And then you do the forward pass, compute the loss, do the backward pass, and then take the optimization step. And then when you finish essentially one epoch, so you've seen the whole data set, you can actually use the validation set to see how your model is performing during the training. And so you can use essentially the same thing. You don't need to compute the gradient. In this case, I think I forgot to put the model in evaluation mode. So this should be model.eval. And then before training, you should have, well, here, model.train. But as I mentioned previously, we don't have any layer that changes the behavior between training and evaluation in this architecture that we defined, so it doesn't really matter. But it will matter probably in other cases, so it's always good to add it. And then for the evaluation set, you do the same thing, get a batch, compute the output, compute the loss. This time is on the validation set. And then you can compute also the probabilities and compute the predicted class to then compute the accuracy. And if you manage to run the notebook, you should get something like this, which we will discuss tomorrow in more detail. But essentially, you see that the training loss decreases, and the validation loss at the beginning decreases, but then starts increasing again. And this is obviously a problem, because it means that your model, the validation loss on your the loss on your validation set is getting worse and worse, which means that the model is overfitting on the training set because it's getting better and better, but then it cannot generalize to unseen data. And we will see how to deal with this tomorrow. And then, yeah, you can revisualize the class probabilities with colors, and you can see that now many of them are actually correct. And at the end, you can show the misclassified example that I saved during the predictions. And you can see that some of them are not super obvious. I mean, dog airplane is probably pretty bad. But yeah, maybe they're quite bad this time. I mean, there is randomly initialized weight, so every time it's different. But maybe this one, deer and dog, is not too bad because it is a dog, but is outside. So maybe many images of deers actually have grass because they're usually outside. So it can be. And maybe this one as well, sheep, is a very bluish image. So maybe the model is thinking that it's a ship because of the background, and the ships are usually at sea, and so that might be why this is misclassified. So you can look at the misclassification and try to understand a bit what's going on. And then, yeah, one tool that you can use in classification is this confusion matrix that essentially plots the true label and the predicted label. And we see that the model is pretty good, so we have most of them in the diagonal, but you can also see some of the classes are confused quite often. So that dog and a cat, for example, are confused quite often, which is probably interesting to know if you want to classify dogs and cats. Probably, again, because they're usually photographed in the same kind of settings. Yeah. Do you have any question? Oh yeah, definitely. Yeah. The solution will be available on GitHub as well. Yeah.
Could you just clarify that if you scroll up until you get to the way you compute the probabilities with the softmax, whatever it is?
Like
It's
this one, for example. Yeah.
Yeah. So in there, I've got 2 equals log max out or something, and it seems to still work. Hold on, I'm trying to find the place where you said there was. You said when you initialize the thingy at the start, you can either use the softmax or you can use the log something. And
Yeah.
You explained it, and I wasn't fully paying attention. Could you just explain that again?
So I mean, you need to compute the probabilities depending on what the output of your model is. So if your model is outputting a linear layer directly, then as we have seen this morning, you need the softmax to get the probabilities. While if your model is already outputting the log softmax, then you can use just exponentiation to get the softmax. So you should adjust this in terms of what you model outputs. Essentially, you can decide if you want to apply the softmax activation function as part of the loss or as part of the model. And then when you use the predictions of the model, you have to know what's the output of your model and then compute the probabilities accordingly.